All right, welcome. This is in-class activity 11B, Introduction to Power Functions. 1. Think of some different types of animals with very thick legs. Think of some very different types of animals with very thin legs. Is it common for an animal with thick legs to have a light body? Is it common for an animal with thin legs to have a heavy body? Why do you think this is? Well, for thick leg animals, whoops, we could, let's see, how about comes to mind is an elephant or even something like oxen. How about that? Birds have thin legs. How about something like a stork or even flamingos? Okay. And we know thick legs are required to carry the weight of a heavy body, and a light body couldn't lift the heavy legs. So it seems as that question is answered. Let's move to objectives for the activity. You will understand how to interpret negative exponents. You will be able to evaluate power functions with negative exponents, describe changes in inputs and outputs of power functions, solve equations involving power functions. Now, in preview assignment 11B, you calculated the stress in structural support columns with different cross-sectional areas. Such columns can fail by collapsing upon themselves if they are not large enough to support the required weight. The following table and graph show the relationship between the stress and the cross-sectional area for a column that is subjected to 150,000 pounds. So here is the table and the graph, and we're going to be referring back to this, but that's the first time we're going to see this. And just give it a second. And what I'm going to do is move to the next question, number 2. It says, how does the value of the stress, that's sigma of A, change as A increases? Do you think that the value of the stress ever reaches 0? Why or why not? So we could say as A increases, I'll even write this down, as A increases, the value of the function sigma decreases. And we could even say it gets closer to 0. It's close to 0, but never equals 0. We'll put that in there as well, but never equals 0. Part 3. Calculate the missing average rate of change of the stress for the intervals given in the table. Express your answers in scientific notation where appropriate. So the first part that's missing, I'm just going to draw an arrow next to it, the first row here. Notice the average rate of stress is empty in that column. So what we're asked to do, the interval for A is 2 to 300. So if I scroll back up to our original table here, and you notice we have the same thing here, 2 to 300. That's what I'm going to be referring to when I write this next information down, and also the 750 and the 500. So if I scroll back down to our next table, what I'm going to do is write the numerator of a fraction as the 500 minus 750, and that's over the denominator, which is going to be the 300 minus 200. Well, if we calculate this out, 500 minus 750, that gives us what? Negative 250 over 100, which ends up being negative 2.50. And that's what I'm going to put in our table, negative 2.50. Let's move to the next missing piece of information. And again, this comes from the above table, the first one that we saw. And where's the 7 and 800? There's 7 and 800. And we're also going to be using this information here, the 214.3 and the 187.5. So let's go with the numerator of our fraction, 187.5 minus 214.3, and that's over the 800 minus 700, and we get a number that's, let's see, negative 0.268. And we can put this in scientific notation. The other numbers in the table are in scientific notation around it, so we can do that as well. And this ends up being negative 2.6 times 10 to the negative 1. So negative 2.6 times 10 to the negative 1. There we go. Now the rest of the numbers are filled out. We work out similarly. I've worked out these ahead of time so you can know the answers. And let me fill these in. This is negative 6.65 times 10 to the negative 2. And then the next piece is negative 2. And that will be times 10 to the negative 2. And there's a little bit more here. The last element in the list, or the last in the table, is negative 6.60 times 10 to the negative 3. All right. So let's scroll up here to part 4. Now part 4, it says write a sentence that describes how the rate of change of the function sigma changes as the area decreases. So we could say something like, as the area decreases, the rate of change of the stress gets closer to 0. There we go. Part 5. The equation for the stress for a column that is subjected to 150,000 pounds is given by the equation sigma of A is equal to 150,000 over A. The function sigma is a power function where the cross-sectional area A is the independent variable. What is the coefficient of this power function, and what is A raised to? So I'm just going to copy this function again. Sigma of A is 150,000 over A. I'm going to rewrite this. So we could write this as 150,000 times 1 over A, and it could also be written as 150,000 times A to the negative 1. So what's the coefficient of this power function? The coefficient is the 150,000, and A is raised to the negative 1 power. Part 6, if a column is under too much stress, it will fail by collapsing or breaking. The amount of stress that causes the column to fail is called the failure stress. Part A, if the stress at which a column is subjected to a 150,000 pound force fails is determined to be 150 pounds per square inch, what restriction does this place on the column's cross-sectional area? So for part A, I'm going to rewrite this as sigma of A is 150,000 over A, and it's telling us that the sigma of A is 150. So I'm going to take this, let me just work across here. The sigma of A is 150, and that's equal to 150,000 over A. And when we solve this for A, we are going to get 150,000 over 150, and this ends up being 1,000, and that's square inches. Part B is worked similarly. It says if the failure stress of such a column is 200 pounds per square inch, what restriction does this place on the column's cross-sectional area? Well, I'll start with the same thing here. And I'm going to solve it the same way. I'm going to take out the sigma of A and write in 200, and then that's 150 over A, solve it for A, and this ends up being 750. And again, it's square inches. All right, so part 7. Let me scroll up here. It says, an architect is designing 2 columns, P and Q, each of which will be subjected to a 150,000 pound force. Part A, the architect calculates that column P will be under 300 pounds per square inch of stress, which is very close to the failure stress of this particular column. What is the cross-sectional area of column P? So I'm going to do the same thing, work these as we did on the previous question. Again, I'm just going to copy this. Sigma of A is equal to 150,000 over A. All right, so again, the sigma of A I'm replacing with 300, and then the rest of this would be the same for now, and that's over A. And then solving this for A, we get 150,000 over 300, and this is equal to 500 square inches. So part B, it says the architect would like to reduce the amount of stress on column P by 50 pounds per square inch. To do this, the architect will design or redesign column P to have a larger cross-sectional area. What cross-sectional area would reduce the amount of stress on column P by 50 pounds per square inch? Well, we could try different numbers for A. So what we could do is write sigma, and instead of A, just try some numbers. Now, if you try a few numbers, you may get a feel for this. And then the rest of this is the same. So anywhere you see the A, you put in 600, and this ends up being 250 pounds per square inch. And we know that 250 is less than 300 by 50. So it looks like this is the correct answer here. The 600 would reduce the number from 300 to 250. Part C, using your answers to parts A and B, complete the following sentence. To decrease the amount of stress by 50 pounds per square inch, the cross-sectional area of column P must be increased by, and this is going to be 100 square inches. So it went from 500 to 600 square inches. Part D, column Q is made out of a different material than column P and has a different failure stress. Column Q will be under a stress of 125 pounds per square inch. What is the cross-sectional area of column Q? So let's do this the same way. Sigma of A, and then we have the numerator of the fraction is 150,000, and then the A. I'm going to replace the sigma of A by 125, and then this is still equal to 150,000 over A. Solve this for A, and I get the 150,000 over 125, and this ends up being 1,200 square inches. Part E, because the failure stress of column Q is very close to 125 pounds per square inch, the architect would like to reduce the amount of stress on column Q by 50 pounds per square inch. To do this, the architect will redesign column Q to have a larger cross-sectional area. What cross-sectional area would reduce the amount of stress on column Q by 50 pounds per square inch? Well, again, let's go back to our function. We could try different numbers. You would quickly get a feel for this, I think. And let's see, take out the A and where we see A, put in 2,000, and this ends up being 75 pounds per square inch. And that's been reduced. That's nice. So part E, let's go to part F. Just going to slide this up a bit. Using your answers to part D and E, complete the following sentence. To decrease the amount of stress by 50 pounds per square inch, the cross-sectional area of column Q must be increased by 800. Again, in square inches. Part G, compare your answers to part C and F. Are they the same? Briefly explain. They are not the same. So let's see. That was C and F. So if I go up to C, that's 100 square inches. Part F is 800 square inches. So definitely not the same. And we could even elaborate a little bit. Because the relationship, okay, the relationship between stress and area is not linear. There we go. All right, so this is the end of the video for 11B, Introduction to Power Functions continued, and thank you.